Exponential growth and decay models, Newton's law, and logistic growth and decay models. Chapter 5, Section 8. Okay, so previously we talked about financial models. Now we're getting into exponential growth and decay, Newton's logistic growth and decay. And these are models that are used all over the place to figure out how things are going to expand or how they're going to decrease and what's going to happen. So these are actually kind of fun. Always want to ask, where are we going to use this? When is this going to become important? And this is an excellent section for showing some of the ways that exponential functions and so power functions, exponential functions, and logarithmic functions are used in real life. And actually at this point in time, because this is being recorded during the COVID-19 pandemic, this is stuff that's being used regularly. In fact, last spring, you would have seen a lot of this where they were talking about flattening the curve. And they're talking about the exponential growth of the pandemic. And these are the types of formulas that they're using. They're looking at what is the growth constant and how can we slow it down? So how can we decrease that growth constant to give time to find a cure and to save people's lives? So uninhibited growth of cells, a model that gives the number n of cells in a culture after a time t has passed in early stages of growth is n of t is equal to n sub 0 times e to the kt, where k is greater than 0. Now, n sub 0 is the initial number of cells. Usually in mathematics and science, when we use a sub-zero, that means the initial value of something, initial velocity, v sub 0, terminal velocity, v sub t, or time or velocity at a given time, v sub t. K is the growth constant. So it's a positive constant that represents the growth rate of the cells. So that's why it's got to be greater than 0. And t is the amount of time that's passed. And then n of t, that function, is the resulting number of cells after that or at that set period of time. So let's take a look at the growth of a colony of mosquitoes. Population of colony of mosquitoes obeys the law of uninhibited growth. If there are 1,000 mosquitoes initially, and there are 1,800 after 1 day, how many will be present in the culture after 3 days? And then second question, how long is it until there are 10,000 mosquitoes? Okay, so we're going to use, this formula. N of t is equal to n sub 0 e to the kt. Now, n sub 0 is the initial number, t is the time, k is the growth constant, and n of t, remember, is the current number of cells. So if we look at this, we see that if there are 1,000 mosquitoes initially, n sub 0, and there are 1,800 after 1 day, 1 being t, 1,800 being n of t, how many there are after that point, and then how many will be present in the culture after 3 days, that's a different value of t. The only thing we're missing here is the growth constant. But we have what we need to calculate the growth constants. Once we have the growth constant, we can put it in, and then we can plug in our other value of t3 and find out how many there will be at that point. And then once we've got that, then we can also deal with determining when there will be 10,000 mosquitoes. So we're plugging in, we know that we started with 1,000 mosquitoes. And after 1 day, we have 1,800 mosquitoes. And see, the only thing we're lacking is K. So we're going to divide both sides by 1,000. And then we need to get rid of that E. So we're going to take the natural log of both sides. So the natural log of 1,800 over 1,000 gives us our K value, because we didn't have to deal with that dividing out the 1 because it was 1. So our growth constant is 0.588. Now that we have our growth constant, we can plug that back into the formula. Now we know that this is our formula for calculating how many mosquitoes there will be at any given time. So we have our initial value of 1,000. We want to see how many we're going to have after three days. So we go through and do the calculation. We find out approximately 5,836. Now with this, round to a whole number, because we can't have part of a mosquito, and we're looking for approximately how many. So rounding up and rounding down, we just use our standard rounding methods. So we're not going to always round up to make sure we count that additional one. If we came out with 5,836.2, round down to 5,836. If we came out with 5,835.9, round up to 5,836. Now, the second question was, when will we have 10,000 mosquitoes? So we know our growth constant, we know our starting point of 1,000, and we're looking for when we have 10,000. So now we're solving for t. So divide both sides by 1,000, take the natural log of both sides, and then divide by 0.588, gets t by itself. Order of operations, 10,000 divided by 1,000 gives you 10, natural log of 10, whatever that comes out to be, divided by 0.588 gives us approximately 3.9 days. Now remember, we're looking for the number of mosquitoes, or the number of days till we have a certain number of mosquitoes. Don't round that to a whole number. Don't make it 4 days. We can have partial days. You just can't have partial mosquitoes. So this is and like I said, this is the type of thing that they used for COVID-19 to determine how fast it was growing and how many cases we would have after a certain amount of time and everything if we were unable to flatten the curve. Flattening the curve, basically what we're doing is the whole idea of this actually is that this is uninhibited, meaning if left to its own devices, this is the growth that will happen. We use this information and then we try to inhibit things and slow it down. So with COVID-19, that was the idea of shutting things down, stopping people being together, putting on masks, using hand sanitizer, and all these different precautions that were put in place. The idea being to slow down the growth and make it so that the curve was flatter, and one thing that a misconception with that is people think, oh, well, if we can flatten the curve, then we've stopped the disease. And no, you haven't. Flattening the curve does not stop it. It slows down the growth. If it's still not stopped in some other way, it will go through that whole growth thing and keep being exponential. By slowing down that growth, we kind of flatten the curve, which gives more time to go in and solve the problem, come up with a cure, come up with vaccines and such, so that less people are affected by it. And in this particular case, that less deaths. Okay, uninhibited radioactive decay. So now we're talking about decay as opposed to growth. The amount A of a radioactive material present at time t is given by A of t is equal to A sub 0 times e to the kt, where k is less than 0. So obviously A sub 0 is the initial amount of radioactive material. K is the negative number that represents the rate of decay. So instead of increasing, we're decreasing. And t, of course, is the time. The half-life of radium is 1,690 years. If 10 grams is present now, how much will be present in 50 years? Okay, let me just explain half-life to you. The half-life of something, such as radium, is the amount of time that it takes for half of the material to disappear or go away. So if you say the half-life of radium is 1,690 years, that means, and we start with 10 grams, then that means in 1,690 years, we will now have 5 grams of radium, half of what we had to start with. So that's what a half-life is. So this is giving us a starting value, 10 grams. It's giving us a period of time, 1,690 years, and telling us that at that time, we will have 5 grams left, half of what we started with. That'll allow us to find our decay constant, K. And then it says, if 10 grams is present now, how much will be present in 50 years? After we've done that, we can say, okay, make the time 50 years instead of 1,690 years and see how much will be left. So let's go through that. So we got our formula, A of t is equal to a sub 0 e to the kt. We're going to plug in what we know. We know we started with 10 grams. In 1,690 years, we're going to have 5 grams. So we only have one thing we've got to solve for. We got to solve for K, our decay constant. So again, divide both sides by 10, take the natural log of both sides, then divide by 1,690, and K turns out to be approximately -4 times 10 to the -4. So negative 0.0004. So that's going to be our decay constant. We can now take that decay constant and plug it into that original formula for K. And now we want to know how much we're going to have left after 50 years. So we started with 10. We've got that in as our a sub 0. We know our decay constant is -4 times 10 to the -4. That's in for K. We're looking for what happens in 50 years. That's T. So now we can do our calculation. Again, order of operations, -4 times 10 to the -4 times 50. Take the exponential of that, multiply by 10, and we get approximately 9.9 grams. So we started out with 10 grams, and 50 years later, we're approximately 9.9 grams. Basically, we lost about 1% is all. So that's why people are concerned about radiation and radioactive materials, because it doesn't dissipate quickly. Newton's law of cooling. So Newton's law was one of the things we're going to cover. The temperature U of a heated object at a given time t can be modeled by the following function. U of t is equal to capital T plus U sub 0 minus capital T times e to the kt. Now, be careful. A common mistake that people make is they like to change variables from uppercase to lowercase or lowercase to uppercase when they're playing with different formulas and equations. And you can't do that because uppercase and lowercase indicate different things. In this case, we see that lowercase t is the time t, uppercase t is the constant temperature of the surrounding medium. So maybe in our case, the surrounding air temperature. So that's what we're looking at. So you have to be careful. There's a difference between lowercase t and uppercase t. So t is the constant. Mu sub 0 is the initial temperature of the heated object. And U of t is the temperature at a specific time. K is a negative constant. This is going to be a decay, right? It's the law of cooling, meaning the temperature is going to go down. So that's why K is a negative constant. So let's look at the cooling time of a pizza pan. Now, this is something that's near and dear to me. I have pizza on a regular basis. We make pizza at home, and the pizza pan's hot when you take it out of the oven, and it cools down over time and get to the point that you can move it with your bare hands. A pizza pan is removed at 5 p.m. from an oven whose temperature is fixed at 450 degrees Fahrenheit into a room that is a constant 70 degrees Fahrenheit. After 5 minutes, the temperature of the pan is 300 degrees Fahrenheit. So we've got a starting time, 5 p.m. We've got a temperature, which we can call the starting temperature of our pan, right? Because if the oven's temperature is fixed at 450 degrees, then when you take the pan out of the oven, it should be at 450 degrees. We have a surrounding medium, air, which is the room temperature of 70 degrees. So after 5 minutes, the time t, the temperature of the pan is 300 degrees Fahrenheit. So we know after 5 minutes, the U of t is 300 degrees Fahrenheit. Question you're asked, at what time is the temperature of the pan 135 degrees Fahrenheit? So it's not after how many minutes, it's at what time. We're starting at 5 p.m. So once we determine how long it takes for it to get to 135 degrees, we have to add that to 5 p.m. And 2, determine the time that needs to elapse before the temperature of the pan is 160 degrees. So now we're looking for a time elapsed for it to get to 160 degrees Fahrenheit. So let's take a look at it. So plugging in what we know, surrounding temperature is 70 degrees. The pan starts at 450 degrees. After 5 minutes, it's down to 300 degrees. So now we start solving for K. And yep, we have to subtract 70 from both sides. Then we divide 450 minus 70 from both sides. And yes, I know you could have done 450 minus 70, come out with 380 and use that as what you divided. I'm just following the whole thing through. So then we take the natural log of both sides and then divide the 5, and we get a constant of negative 0.1004. I intentionally kept it out to that 0.1004 because I wanted to show it wasn't exactly just negative 0.1. And it did continue on from there too. So now we're going to plug that in for our constant K, and we want to find out how long it's going to take to get to 135 degrees. So again, the initial temperature was 450. The surrounding ambient temperature is 70 degrees. We've got our cooling constant, that negative 0.1004. And we're looking to see when the pan will be 135 degrees. So we'll have to do the same thing. Subtract 70 from both sides, divide by 450 minus 70, take the natural log of both sides, divide by that negative 0.1004, and get our time. And our time is 18 minutes. So now that we know our time is 18 minutes, what time will it be? And I don't have this shown on the slide, but we started at 5 o'clock. So if it took 18 minutes for it to cool down to 135 degrees, then at 5:18, it will be down to 135 degrees. Now, I don't know why 135 degrees was chosen. Maybe that's considered to be a temperature where it's considered to be bearable for someone to pick it up with their hands and move it around. I don't know, but it works for the problem. Now, the second part of this was how long would it take for it to get to 160 degrees? So same thing as we just did with 135, except now we're trying to get U of t to be equal to 160. Again, subtract 70 from both sides, divide by the 450 minus 70, take the natural log, divide by negative 0.1004, and we get a time of 14 minutes. So obviously, since it started at a higher temperature and we were talking about cooling, it's going to take less time to get to 160 degrees than it did to get down to 135 degrees. I don't know why, but that example just made me a little bit hungry. Now the logistic model. In a logistic model, the population P after time t is given by the function P of t is equal to C over 1 plus A times e to the negative bt, where A, B, and C are constants, with A greater than 0, C greater than 0. The model is a growth model if B is greater than 0, and the model is a decay model if B is less than 0. You may be thrown off a little bit by that. Wait a second. If we're dealing with a growth model, what's going on? We have a negative B here, a negative B in the denominator here. What's going on? If it's a growth model, shouldn't that be negative? No, remember, we're in the denominator, just as I said. If you were to move that into the numerator, that would be a positive exponent. So growth will be positive for B, decay will be negative for B. So let's do a fun one with this. Birthdays. Logistical model P of n is equal to 113.3198 divided by 1 plus 0.115 times e to the 0.0912 n. Models the probability that in a room of n people, no two share the same birthday. Now, you may have heard of this before and seen how this works. If not, this may be a shock to you, because how many birthdays are there possible? Technically 366, right? Because there's the possibility that someone was born on a leap year. So when you look at that, you go, well, what's the probability? In here it says, in a room of n equal to 15 people, what is the probability that no two share the same birthday? Well, if you're talking about 15 people and there are 366 possible birthdays, it seems very unlikely that any two would share the same birthday. But we're going to take a look at this and see, well, what is the probability that no two share the same birthday if you have 15 people in that room? The other thing we're going to look at is how many people must be in a room before the probability that no two people share the same birthday falls below 10%. So basically, how many people do you need in the room to make it 90% certain that at least two people are going to share the same birthday? So let's look at that. So we're looking for, if we have 15 people in the room, what's the probability that no two share the same birthday? And we plug that in for our number n there, and we get 78.1%. So what that's telling us is that you have nearly a 22% chance with only 15 people in the room that two of them are going to have the same birthday. Think about that for a moment. You've got 15 people in the room. There are 366 possible birthdays, and you already have almost a 1 in 4 chance that two people in that room are going to share the same birthday. The second question was, what's it take to get down to a 10% chance that nobody shares the same birthday? So we're going to solve for that n, which means we get into this ugly formula, right? Because we're going to need to work our way through to get to that n. So I multiply both sides by 1 plus 0.115 e to the 0.0912 n, and then I divide both sides by 10, and then I have to subtract the 1, take the natural log of both sides, divide by 0.115, and then I divide out my 0.0912. And we find out that it comes out to be approximately 49.32, or if we have 50 people in the room, then we only have a 1 in 10 chance that nobody shares the same birthday. With 50 people in the room, we have a 90% chance that two people are going to share a birthday. Something you can do on your own: plug in 50, see how many people you need to have in the room to come out with a 50% chance that nobody shares the same birthday. Because that's your break-even point. You find that out and you see, okay, if you've got a room with that many people or more, or I should say with more people than that, then you're more likely to have two people share the same birthday than you are to not have anybody share the same birthday. And you can see that we got down to a 10% chance of nobody sharing with 50 people. So it's going to be a lower value than that. We were at a 78.1% chance with 15 people. So somewhere between 15 and 50, we're going to hit this magic number. So try that on your own. Give it a shot and see what it comes out to be. Now, finally, we're just going to talk about the properties of the logistic model. First of all, the domain is the set of all real numbers. The range is the interval from 0 to c, where c is the carrying capacity. We're not going to go more in depth in this, so don't try to dig too much or ask me a lot of questions about this. If you want to know more, you can go online and you can look it up that way, but we're not going to focus on it in this class. There are no x-intercepts. The y-intercept is p of 0. There are two horizontal asymptotes, y equal to 0 and y equal to c. Now again, we said there are no x-intercepts, right? Well, here we say that there's a horizontal asymptote at y equal to 0. That's the x-axis, right? So it will approach but will never touch the x-axis. It will also approach but never reach the value of c, the carrying capacity. If you think about that capacity, that's how much can it handle? It gets to the point where it just can't hold anymore. P of t is an increasing function if b is greater than 0 and a decreasing function if b is less than 0. Remember, we said if b is greater than 0, then it's a growth constant. If b is less than 0, it's a decay constant. There is an inflection point where P of t equals 1/2 of the carrying capacity. So when we get halfway to the carrying capacity, we're going to have a change in the curve. And as I state here, the inflection point is the point on the graph where the graph changes from being curved upward to being curved downward for growth functions, and the point where the graph changes from being curved downward to being curved upward for decay functions. And remember, we have that range from 0 to c. So basically, you're going to see this graph. It's kind of going to look like a sideways cubed function. You're going to see it decreasing, and then the curve will change, or you're going to see it increasing and the curve will change. So you'll see this little wiggle in it. And the graph is smooth and continuous with no corners or gaps. So just the properties to understand of the logistic model. And that gets us done with these exponential models, logistic models, and Newton's law.